Okay. Thank you, Mr. Chairman. Good afternoon, everybody. I'm going to present a subject which is quite different from all the previous presentation. Anyway, I try to describe with a unified approach both failure in continuum material, both solids or liquids. So let's start by considering a very simple classical relation which enable us to assess failure in solid materials. We can consider classical plasticity theory or more recent studies on crystal plasticity, so we can change the scale of the observation of the phenomenon. And moreover, we can consider fracture mechanics as another way of failure in solids. And another, as before, we can consider different length scale of observation. So we can deal with macroscopic or microscopic or even nanoscale fracture mechanics, like the very recent researchers have shown to be able to describe very well the phenomenon. So if we consider collapse in liquids continuum, we have to deal with the so-called cavitation phenomenon, which can be, for some aspect, to be considered very similar to other kind of collapse that we can meet in other kind of continuum materials. So let's consider first the failures equation in solid materials. We have just recall simple relation for plastic collapse. For example, I consider here the Drucker criterion, which is a very general criterion, which takes into account both the hydrostatic and the distortional contribution of the stress state inside the material. So we deal with different kind of materials with the same load by properly setting the parameters which are involved. This is another expression of the same criterion, and which is more easiest related to the tensile and the compressive yield stresses of the material. But anyway, the same description of this kind of collapse, which is a kind of plastic flow of the material. If we consider fracture collapse, we can have brittle fracture when we are in the context of inelastic fracture mechanics, and we can decide if the material is going to break or not, depending, for example, of the one parameter K1, or by using the Griffith criterion by considering the energy and comparing it with the critical energy, the critical surface energy of the material we are dealing with. But we can have also ductile fracture, so we can have the appearance and growing and coalescence of voids inside the material. So this is another kind of failure which can appear very often in non-pre-cracked materials. In this case, this very simple law I will describe later, consider the first principal stress and compare with this quantity, which is a characteristic parameter of the material, sigma n, and the area that is between the voids that develops inside the material. This is called the Thomson law. So, speaking about brittle fracture, we are able to distinguish between fracture-like collapse or plastic-like collapse, depending on the size of the pre-crack which is present in the material. So, we want to develop a very simple equation by considering the main characteristic of the stress field. So we introduce simply the hydrostatic stress, which is the trace of the stress tensor divided by 3, and we can define also the very known triaxiality factor, which expresses the ratio between the volumetric contribution of the stress state and the distortional contribution of the stress state. So we can have a very known situation, for example, pure shear stress, we have triaxiality equal to 0, pure hydrostatic stress state, we have infinity value for the triaxiality, and uniaxial QD stress state, and uniaxial QD stress state. So now I want to consider the very simple 2D problem. So in the further slide I will talk about just 2D problems. In this case, we are able to express the principal stress of the stress tensor as the sum of the principal stress of the deviatoric stress tensor plus the hydrostatic stress K, which I have defined before. And in this way, we are able to obtain this very simple equation in which we have only J2 and T. So in the next expression, we will use always this relation to express the maximum stress. If we consider fracture-like failure, by using this definition of the maximum stress, we can write the relation which describes the failure in the case of brittle fracture, for example, by comparing this quantity with energy terms, for example, or the critical stress intensity factor, or in the case of material without any crack, we have to compare with the maximum tensile strength of the material. So in any case, we have a single relation which describes the failure of the material by using just these two parameters of the stress field. On the other hand, if you consider ductile fracture, we have fracture due to the development and coalescence of voids after the formation of a macroscopic crack. And in this context, we can use, for example, some simple void model like the Raisen-Tracy relation, which relates the size gradient of the voids with the plastic strain and with the stress fractionality. But the critical condition can be considered to be this equation in which all these voids undergoes coalescence, so we have the final rupture of the material. And the law I have mentioned before, derived by Thomson, can be rewritten in this form, where once again we have the term that I have expressed, and which is similar, of course, in this context to the other expression. If we consider plasticity-like failure, and also we have the Draper criterion once again, we are able to express the same critical condition through these two parameters, J2 and T, and at the end we can join together all the above relation in one simple expression in which we have two material constants, beta and B, and the other two terms which characterize the stress field inside the material we are dealing with. So let's move to consider the collapse in liquids. Here the situation is a little bit different because the stress state inside the material can be written as the sum of a so-called hydrostatic stress state plus another term which depends usually on the velocity field inside the fluid. So the tensor tau is written, for example, for Newtonian liquid in this very simple way. Tau equals to a constant which contains the dynamic viscosity of the liquid times the symmetric part of the gradient of the velocity field inside the liquid. This is a very simple relation which is valid for a limited class of liquids, but not for every kind of fluid, of course. So if we consider, for example, incompressible liquid, we have this relation that must be satisfied. So divergence of U must be equal to 0. That is to say, this is the conservation mass law. And in this case, we have that the trace of the tensor tau is equal to 0. So we have no contribution due to this term to the pressure inside the liquid. The same thing we can say for a liquid under starting conditions. So we have a liquid at rest, which has 0 velocity field, so of course we have tau equal to 0, and we have only the hydrostatic pressure inside the fluid. So the problem is, in general, in the flowing liquid, the pressure, the mean pressure, is not just given, but the stress tensor sigma, but also by this other component of the strength tensor, which depends on the constitutive relation of the liquid. So this is a kind of constitutive relation for the liquid like this. So in this case, we have to make some different consideration in order to manage this kind of continuum material, which is not really a solid, but something different. So, Stein phenomena, I stated before, is usually identified as the cavitation, which occur when the pressure in one point on the fluid is higher than this characteristic value, which is called vapor pressure, which depends on the temperature. So, of course, I have not mentioned that we consider P as negative when we have tension, because in fluid mechanics we have the opposite assumption for the sign. So we have, when P is less or equal to Pc, we have cavitation, and on the other hand, when P is greater to Pc, we have no cavitation. So this Pc is a cavitation threshold negative pressure, which must be specified for each continuum we are considering. So, what is not true in this relation is that it's not correct to use the mean stress inside the continuum. But we have to use the maximum principal stress instead of P, because as I have shown before, P depends on the constitutive relation of the liquids. So it's not a parameter which is uniquely dependent on the stress state, but also on the kind of liquid you are dealing with. So it's more correct to use the principal stress instead of the mean stress, even if many times cavitation has been assessed by using this parameter. So we can say that in a flowing material like liquids, the pressure P has not meaning. So we can say that the liquid is not able to average the stress. So we must consider the maximum principal stress instead of the pressure P. So we can consider, for the case of liquid, the general expression of the stress tensor for 3D or 2D cases. We focus on this second case, and we have the hydrostatic part, you can say, and the other one, which depends on the shear stress which develops inside the liquid. So we are able to write again the maximum and minimum principal stress of the dilatoric stress tensor by combining properly the stresses, the principal stresses of the stress tensor in the material. And we are able to rewrite again the cavitation condition by using this principal stress instead of the mean stress or the pressure inside the liquid. So we obtain this relation where we have sigma 1, and for example, if we express the shear stresses by means of the Newton relation, we can relate directly the condition of cavitation with the velocity which is inside the liquid. I will show you a very simple example at the end of the presentation. Like in solids, we can also observe that if the liquid contains impurities or bubbles or small particles, the cavitation phenomena is facilitated. So we can define, instead of the vapor pressure of the liquid, another parameter which is very similar to what we use normally in fracture mechanics, which depends on the size of the initial imperfection which can be contained in the liquid itself. So the condition can be expressed exactly as before in this way, where we have to choose between these two parameters depending by the kind of liquid, if we have or not impurities inside. So if we have the condition that the maximum principal stress for example, sigma 1 is greater in absolute value to the vapor pressure, we have the development of a detachment of the liquid. And moreover, if the liquid is flowing, usually we have rotating particles which develop a very big bubble which fills with the gas of the liquid. So you can say here some example of developing of such kind of failure inside the liquid, which must be carefully considered because they are responsible, for example, for the so-called cavitation corrosion, which is a very important phenomenon for all the solid surfaces which are in contact with these failure zones. So, if we define again for the liquid the stress reactionality in the same way as before, the only difference is the minus because of the convention we used, and we express the J2 term of the vectoric stress tensor, we are able to write again the critical condition which describes the failure of the liquid in this way, and again the expression has the same structure apart the sign which appears here inside the parentheses. So we have some simple cases. For example, for pure shear we have cavitation when the square root of J2 is greater or equal to PC. In the case, for example, of high level of hydrostatic compressive pressure, that means T greater than 0, very greater than 0, we have sigma 1 negative, so we have never cavitation, and the failure in the liquid doesn't occur. Here are some examples of rupture of solids with ductile, pre-cracked ductile, brittle solids, and some example of cavitation which develop in the liquid due to the fulfillment of the condition I stated before. So, the relation which join together all the cases I examined is finally this one. I have this term, J2, square root J2, which multiply beta plus alpha t. And depending on the problem I'm considering, we have to choose just the coefficient from this table, depending if the solid is brittle, if the solid is fluid or not, or in the case of the liquid is perfect liquid or with the inclusion and so on. So the relation can be represented in this graph, in which we have the case of solid, different solids here, and the case of liquid. So the trend is very similar. We have failure here for pure shear, for a liquid, when we reach the pressure, the vapor pressure threshold for fracture. While in the case of solid, we have, of course, to decide the parameters which are characteristic for the solid. So this is a very simple example just to compare the two approaches I just explained. We have a solid strip under shear load and under downward gravity load. And here we have a 2D fluid flow under velocity field, a horizontal velocity field which is distributed in a linear way under downward gravity load. So we have no pre-crack, so we can expect the failure in the solid will appear as the appearance of voids and subsequent coalitions of voids up to the formation of the macro crack. So I have here the detail of the stress tensor inside the solid, starting from the simple linear elastic solution, and we can write three different functions which define the failure situation for brittle material and for ductile material. Here, when the collapse is due to plasticity, and here when it's due to void coalitions, so but are very similar. In this case, we can observe that failure is more easy occur at the bottom of the strip when we deal with plastic material. Otherwise, we have more easily fracture or tensile rupture of the material at the surface when we consider brittle materials. The same thing we can do for the liquid by using a simple Newton law for describe the relation between shear stress and the velocity gradient. We get the equation we describe the failure possibility that is given by the function f1, and here we can observe that the collapse due to cavitation should occur at the top of the surface, so where the pressure is equal to 0, and we have only shear stress due to the moving of the surface of the liquid. Okay, just a few conclusions. So I tried to present a unified approach described with a simple relation, both failure in solid and in liquids, but with just a couple of parameters, the stress flexuality and the distortional energy, we can gather together all the expression that we can usually encounter in assessment of failure of continuum materials, and by properly setting the material parameters, we are able to describe and to predict which is the more probable failure type of the materials under consideration. This unique approach can be used, for example, for the assessment of particular materials such as powder materials, which share common aspects of both solid and liquids. Thank you.
Any question? What does it mean elasticity for a liquid? What does it mean plasticity?
I think a liquid can be considered to be like a brittle material.
Brittle material?
Yes, because it fails under a condition which is really exactly as in a brittle solid. So you have only one parameter, Pc, which determines the temperature. But if you reach that value, you will open a bubble in the liquid. So I can mean that you cannot have a sort of plasticity in the liquid.
How would you find that point in a structure where your criterion should be applied? Because you have a stress field.
This is just a basic theory to gather together all these previous theories, but not just to assess exactly where it can happen. But you're right, I have to decide where to check.
Other question? No. Thank you very much.